Good evening, everyone. So, Bhageshri, should we start?
Yes, ma'am.
Yeah. So, as you all know, today's topic is causal DAGs, which is the directed acyclic graphs. So, when we are talking about causal associations, the traditional framework which is used is known as the potential outcomes framework or the Rubin causal model, about which you will have to read more because this will not be covered in this particular session. But however, in this model, we define the causal effects as the difference between two hypothetical states which are counterfactual. Counterfactual means you have a group of people, say XE, whom you compare with, you want to actually compare the same group of people. So XE is, for example, a group of people who experience the intervention, and ideally you would like to compare them with themselves at the same time but without the intervention. That is known as a counterfactual, but that is impossible. So when you want to say that whatever change has occurred because of the intervention, essentially you should compare the counterfactual states, but in reality that is not possible. So a solution we have come up with is the randomized control trial, hoping the randomization will make the two groups similar to each other with respect to known as well as the unknown confounders. Now, when we use this framework, that is the Rubin causal model and the randomization process, such causal inference relies on estimating averages across groups, and this is what actually this Rubin causal model actually explains in detail. But this is not possible for many research questions, for ethical reasons, for operationality limitations, or because it's not feasible to carry out a randomized control trial. And then we have no other option but to rely on observational studies. Now, with observational studies, one of the key challenges which we face is how are we going to handle the confounding here? Because in randomized control trials, randomization was the heart of the trial which helped us deal with confounding. But how do we do the same for observational studies? And in epidemiology, we have been taught that we identify and handle confounding in the design and the analysis phase. So there are various ways in which we do this. One of the challenges, however, could be to identify potential confounders. Now, how do we identify these potential confounders? So we all know that there are different ways of identifying confounders. Our knowledge of the subject matter, our research question, the review of literature, our understanding of the topic and the biological plausibility, and the clinical expertise. As well as we know that there are some statistical techniques to identify confounders. So in many articles, we read that in our first, bivariate regression, if the p-value of the association is statistically significant, we say we included it in our multiple logistic regression model. Another criteria could be if the odds ratio after adjustment for a particular covariate changes by 10% or more, we would consider it as a potential confounder and include it in our multiple regression models. And what we are going to study today is another method of identifying confounders, and these are known as the directed acyclic graphs. Now, if we look at this example, the research question, does regular physical activity reduce the risk of hypertension? Then, naturally, if we ask ourselves what are the variables for which we would like to collect data, we would like exposure, which is the physical activity here, and the outcome, which is the hypertension. Now, do you think there are any other variables for which you would like to collect data?
Yes, ma'am. Like we can say dietary, like increase in salt intake, or they are taking salt after preparation of vegetables.
Okay, so one you are saying is the diet. Okay, any other?
Obesity, ma'am.
Obesity, okay,
Sleep, madam. Sleep hours.
okay,
Increase in stress.
stress, okay,
Yes.
any other?
Age.
Yes, so we all know age is something which we would like to look at for nearly all the associations, right? So why would you be interested in collecting the data on all of these variables, not just the exposure and the outcome?
Ma'am, there can be a confounder or an effect modifier or a mediator.
Correct. So we think of all of these variables as potential confounders, and we would like to include them and adjust for them is what is our thought process, right? So there could be many of these variables which we will jot down, we will review literature, we will try and understand the association, what is our understanding, and all of these. So the question is now we would have a very long list of variables. So would you adjust for all of these variables? Because we have already discussed actually, but I just want you all to think, because today's article is just going to really help us the way we think, develop the way we think about causal association. So my question is, would you adjust for all of these variables, or will you pick and choose some of these variables? What is your thought about that?
We will try to pick some variable, ma'am.
Yes, which ones would you pick?
The one which can be probable confounders.
Yes. And how would you identify that?
By manually seeing if each of the variables are related to each other.
Okay. So you would say that we would not include all of this blindly, but we would do some statistical analysis before deciding which ones to carry forward as potential confounders,
Yes, ma'am.
right? Now,
Yes.
supposing, yeah, yes,
Thank you.
yeah. So supposing we have these different researchers and they think differently and they decide, okay, let me use these combinations of variables. So we observe that the uh, odds ratios which we are getting are very much different from each other. So if it's just adjusting for age and sex, then the physical activity seems to be protective, and all of these are of course showing a significant protective effect. Physical activity is protecting against hypertension. So what do you see with adjustment for age and sex? Odds ratio of 0.34, right? But as soon as you add BMI, the protection effect seems to reduce. But when you remove BMI, you add health checkup, it increases further. And then when you use all of these four in the model, again you get an odds ratio of 0.32. So which of these you think is the correct uh, researcher's approach? Which is the approach which is correct? One, two, three, or four? So what I'm trying to say is that, see, there could be many variables you can adjust for in your model. So how do you decide? Because it is very crucial, because the adjusted value which you get are going to be very different from each other, and the inferences which you draw are going to be very different from each other. So the take-home message is that you have to be very, very careful when you develop your models. And that is where these DAGs help us. So DAGs are nothing but directed acyclic graphs, and our learning goals are actually to understand what DAGs are, what are they useful for, and how these DAGs help us to develop our regression model or to think about our analysis, especially about which variables to include in a regression model and which should not be included in the regression model, and then how to construct a DAG. So we are going to understand DAGs from these angles. So many of you all are really requesting me to go ahead with regression and discuss regression models. But before we go ahead and understand how to do regression, we should understand how to develop a model and decide which variables should be included in our regression models. So these DAGs help us in that direction. So we say that DAGs are directed. Directed means what? Directed means there are arrows, and hence the word direction, directed, comes into picture. Acyclic means that these arrows, they do not go around and come back to the same point. So they are acyclic. There is no cycle which you can complete in the DAGs. So we say it is acyclic. And of course, they are the graphical representation of the assumptions which we make when we develop our model. So which of these two do you think are DAGs? The top one or the bottom one?
Ma'am, top one.
मॅम
Yes. So,
मॅम
yes,
तुमचा आवाज ऍक्च्युली डबल येतोय.
माझा आवाज. Everyone, for everyone?
No, ma'am.
No, ma'am.
Bhageshri, you have multiple devices open at your end.
Okay, ma'am. Okay.
Yeah. I think it's not a problem for anyone else.
No, ma'am.
Yeah. So it's a graphical presentation, and you can see that the top one, it is acyclic because you can see that the cycle never gets completed, while the bottom one, it's a cyclic graph. So what we are looking at are acyclic graphs, and therefore they are known as directed acyclic graphs. Now, what are the components of DAGs? So there are nodes. Each node represents a variable in your model. So these can be measured or unmeasured constructs. Usually you will see that in DAGs you have the measured constructs which are included. There are other models which are similar to DAGs in which there are latent variables about which I will not touch upon now. Then there are arcs or the arrows, which are also known as the edges. So these are the directed arrows which are showing the direction. And whenever a direction is shown, it actually indicates a causal relation in a DAG. And a DAG is a non-parametric representation of our thought process when we are developing our causal model. Now it is non-parametric because actually there are no measurements here, but it is all qualitative. It is just a qualitative representation of our thought process. So we do not commit upon the type of relationship, that is whether it is a logistic or a linear or a quadratic relationship, nor do we talk about the estimates of the various associations of the various variables in the model. So these are just showing us the causal relationship that A or C is causally related to E is causally related to O, etc. And then, of course, there is a path. Path is any arrow which grows from one node to the other. So whenever there is one arrow which is shown, usually that is called as a path. So you have a node and you have a arrow or an edge or a arc and a path. Now this path which is there are different types of paths. Two main types of paths which you see in a DAG are the directed paths and the undirected paths. So in the directed paths, when all arrows are pointing in the same direction, then it reflects what is a causal relationship. So there can be a directed path, like from screen time to obesity. So screen time is directly causally associated with obesity. or it can be an indirect directed path in which there is something else, what is known as a mediator. So screen time affects physical activity and thereby it affects obesity. So this is an indirect path where there is a mediator. But both of these are directed paths. And whenever you see a directed path in a DAG, it indicates a causal relationship. And these arrows which point in the same direction, they are known as open paths. So these paths are open in the causal pathway. So naturally, if you have directed paths, you will also have undirected paths. So there are different kinds of undirected paths, the backdoor path and the collider. So this is a backdoor path. What is a backdoor path? You have two variables which share the same cause. So you have parental education, which is a risk factor for obesity, and parental education, which also affects screen time. So screen time and obesity are connected to each other by what is known as a backdoor path. This is a non-causal path. It is an undirected path, but the two are connected to each other by this backdoor path. And if you remember our session on confounding, this backdoor path always represents confounding. So this structure, wherever you see this backdoor path existing, these are alternative ways in which exposure and outcome are associated with each other, and all such variables which are in a backdoor path represent confounding and are potential confounders. So in this picture, what you see is that physical activity it is a mediator and parental education is a confounder. Are you getting me here?
Yes, ma'am.
Yes, ma'am.
The next backdoor path which we are looking at is a collider. Now, what is a collider? Any variable on the path in which two arrows are entering it or are pointing towards it. That is, there is a collision of two arrows, that is known as a collider. It means that two variables have the same effect. That is screen time as well as obesity. Both can lead to self-harm. So self-harm is a collider for the exposure and the outcome. Now, whenever there is a collider, that becomes a closed path. Now, an open path means what? Open path means that the association between the two variables is transmitted through a backdoor pathway. A closed path, collider is a closed path, means that the association between the two variables, in this case the exposure and the outcome, cannot be transmitted through a collider. That is known as a closed path. So this is something which is difficult to understand. I will go a bit slowly here. That is, remember that if you have two variables and both of these exposure and the outcome are a risk factor for a third variable, you should not touch that variable in your adjustment. If you adjust, because this is a closed system here, that is your screen time, obesity and self-harm. No association is transmitted as long as you leave self-harm alone. If you try and adjust for self-harm, you are opening this channel and you make screen time and obesity associated with each other. So this is what we will be studying in the upcoming slides. The only thing I want you to remember is to understand what a collider is at this point in time. That is, if the exposure and the outcome both are risk factors for a third variable, that becomes a collider. And the collider, if it is left unto itself, it is a closed path and it will not actually be similar to a confounder. That is, it is not going to lead to any alternative explanation of association between screen time and obesity. So this is the fundamental structure. If you see, you have the nodes here, the exposure, the outcome, and the mediator, and there are directed paths. That is, in the directed path also you can see that there could be a direct association of the exposure and the outcome. or there could be this association or this causal association which is mediated through a mediator. Sometimes it can be both. The exposure can have a causal association directly or through the mediator. And then there are other variables which can be confounders or colliders. So this picture, are you understanding this picture properly?
Yes, ma'am.
So you have in your analysis, especially if your research question, you have identified clearly an exposure and an outcome, and you want to see the association between the exposure and the outcome, and you are doing observational studies, then it's a good idea to first draw your DAG. First, ask yourself whether you are interested in the total causal association, that is the direct as well as the one which is through the mediator. Then you should also look out for all the potential confounders. And is there any other variable which is the result of both the exposure and the outcome? So these things, because have to be jotted down in your DAG very carefully, because they help you in your decisions about the variables which you will adjust for in your analysis to get the strength of association between the two variables you are interested in. So I told you, you have paths which are open paths, and these allow statistical association or information to flow between the variables. Now, what does this mean? Allowing statistical association to flow, it means that if you know the value of one variable, you will be able to predict or tell the variable or guess the variable, the value of the other variable. That is, if you have the value of the exposure, you know what the value of the outcome will be. That is possible in an open path. In a closed path, such associations are not transmitted. That is, you will not be able to make any comment about the outcome even if you know what the exposure variable is. So are you understanding the difference between this when I say what is the open, if I say open path, what it means, and if it's a closed path, what it means? So if I say that physical activity and obesity, this is an open path. If I know physical activity, if I say it's binary 0 and 1, and obesity is 0 and 1, after my analysis, if I find a causal association, then if I know the value of physical activity as 0 and 1, I will be able to tell whether the outcome for that person could be obesity or no obesity. So if I am able to guess or predict the outcome based on the value of the exposure or one variable based on the value of the other variable, I say that statistical association is permitted to flow, and that is an open path. If I am not able to make such statements about associations, that becomes a closed path. So we will see further with examples. Hopefully you'll get some more clarity. So when you look at the various paths, when you have a mediator, that path is open. When you have a confounder, that path is open. But whenever you have a collider in your DAG, that path is a closed path. So without any adjustment, this is just that the variables are there. You are not doing any adjustment. So in that state, there are these mediators and confounders contribute to open paths while colliders contribute to closed paths. This is what you need to remember. So what are the rules? The rules when you're drawing DAGs are that all backdoor paths, that is your confounders, are open paths. Paths with colliders are closed paths. Paths without colliders are open paths. No directed path in a DAG can form a closed loop. That is why it is a cyclic graph, because there is no feedback loop. And if you say the path is a directed path, it has to be open. So for all causal associations, your paths need to be open, and the non-directed path. So when you have your final DAG, these two rules you should remember, that the directed paths have to be open, causal paths have to be open, and the non-directed paths have to be closed. So in the previous graph, you will see you would want to keep the path from exposure to outcome either direct or through the mediator open, and you would want the confounder and the collider to remain closed in your final DAG, because you are interested in the association between exposure and outcome. You do not want any other paths to be open. So this is something which you should remember when you're drawing your DAG for your causal association. So usually that means that, now when I say this open and close, remember what happens is that your adjustment or your analysis in the previous graph, all you need to do actually is to identify your confounders and close these open paths. So I just so you want to keep this path open, this path open. You want to keep this path closed. So all you want to do when you do analysis is to convert this open path into a closed path. And how do you do that? You do that by adjusting for the confounders. So you can adjust for the confounders as you have been taught by either, say, restricting your study group to a particular strata, or by stratification in your analysis, or by regression in your analysis. So you want to identify these confounders and you want to adjust for them in your design or analysis. And also you have to identify your colliders, because these colliders are closed in the beginning itself. You do not want to include the colliders and adjust for them, because this will be an error you will be committing in your analysis if you include a collider in your regression model. So inadvertently, if you include a collider as a confounder and adjust for it, then you are not in a position to come up with the right causal estimate. Are you understanding this much?
Yes, ma'am.
So I'll tell you an example which will help you to understand with the help of a confounder and a collider. So mediators, if you identify that one variable is a mediator between an exposure and outcome, you should not include it in your model and adjust for it. Confounders, you should include and adjust for them. Colliders, you should not adjust for them. And when I say adjustment in the world of DAGs, that is also known as conditioning. So you condition only for confounders. You do not condition for mediators or for colliders in your model. So as I told you, you want this to be open and you want all the directed paths to be open, and you want to close the non-directed paths when you plan your study, design and analysis. So what do you do in your analysis is change the status, that is open to closed, for your confounders, because these are the biasing paths and you want to block all these biasing paths in your DAGs. So when you want to have an unbiased effect estimate between the exposure and the outcome, you want to condition and adjust for the potential confounders. And when I say, whenever I pick up a variable and I condition for it or I adjust for it, I change its status. I change the open path to a closed path, and I can change a closed path to an open path by conditioning. So this is something you should remember. If you include any variable and adjust for it either by restriction, stratification, or by regression, you are changing the status of the path in the DAG. If it is open, it becomes closed. If it is closed, it becomes open. So the conditioning, the adjustment, or the controlling, these are the different words which are used, which are synonymous to each other in the study design or analysis. This, whether you want to adjust or not, will depend upon whether your variable is on the path that is a mediator, whether it is a backdoor path that is a confounder, or whether it is a collider. So once you get clarity about what kind of a variable you are dealing with, then you will be confident of whether to include and adjust for that particular variable. So we'll just go through each of these once again. So confounders, as we saw, was causes of the outcome that are associated with the exposure. So you have some variable which is a cause of the outcome as well as associated with the exposure. This creates what is known as a fork structure. So in DAG language, in many literature, this is described as a fork structure and a backdoor path between the exposure and the outcome. So this all the arrows are moving in one direction, but you have at least one arrow which is moving in the opposite direction, then it is a backdoor path. And when you do conditioning, that is your adjustment, say through regression or by restriction stratification, you close the open path. So if you say parental education, higher screen time, higher obesity, and you find an association between higher screen time and higher obesity, an alternative explanation could be the higher parental education and not higher screen time per se. So when this backdoor path comes into picture, this is a confounder. And if I now do stratification for adjustment, or if I do restriction or regression, then what I'm doing is I'm just controlling for parental education. I say that children with similar parental education, what happens in them with regards to screen time and obesity. So after adjusting for parental education, if I still find an association between screen time and obesity, I say that there is a positive causal relationship between screen time and physical obesity after adjustment for parental education. That is, I have closed this path and I'm purely looking at this causal path by adjusting for the potential confounder. The next, so this is an example in which it was thought that paracetamol use increases the risk of development of wheeze in the follow-up period in the pediatric age group. But later on, with further analysis, it was seen that viral infections led to a backdoor path between paracetamol use and later wheeze. And when the analysis was redone after adjusting for this potential confounder, there was no association between paracetamol use and development of wheeze in the follow-up. So all of this causal association was attributable to viral infection. This association no longer existed when you conditioned on the potential confounder, which was associated with both the exposure and the outcome. Are you getting me here?
Yes, ma'am.
Others in the group?
Yes, ma'am.
Yes, ma'am. Our job is to find these, the variables on the backdoor path and condition on them in our design and analysis. Otherwise, we will be making a gross mistake by saying that association exists when it in fact does not exist in reality. So again, this is another example in which the antenatal steroids were not found to be associated with BPD, but several mechanisms, there was biological plausibility by which the reduction was possible, but only after adjustment of potential confounders was this association proven. So invariably nowadays, it is very common that we do not just look at two variables, exposure, outcome. We are always interested in looking at other variables and adjusting for them. Now, this mediators is another important or interesting thing which nowadays is coming up in a big way, because when you are interested in exposure and the outcome, I told you that this can be a direct association or it can be through a mediator. So what is the kind of analysis in which you want to differentiate how much of this causality is direct and how much of it is mediated through a mediator, that is known as mediation analysis. So supposing you are interested in the total causal association. So we will stick to scenarios where we are interested in the total causal association, direct and indirect. In those scenarios, these intermediate variables which are in the chain of causality are not adjusted for, because when you adjust for this variable, you will close this pathway. Then the only pathway which remains is if there is any direct association of screen time with obesity, which does not go through physical activity. So usually when you are interested in the total association, you do not adjust for any mediator. This is what you should remember. Mediation analysis is altogether different topic, which I am not touching upon. Then coming to colliders. Now, colliders, I told you, supposing screen time increases the risk of self-harm, obesity also, or say obesity is another reason for increase of self-harm. So both of these are colliding, the exposure and the outcome with self-harm. Now, supposing you decide to restrict your study amongst children with a history of self-harm. Now, what does this mean? This means that as soon as you do any kind of adjustment, because it is easy to understand, I am using in the design phase restriction. I told you we open the channel for association between exposure and outcome. So if in a child with a history of self-harm, there is no history of screen time, I can guess that there is higher chance of history of obesity. So by adjustment or by restricting to a particular group, I am able to make an association between these two. That I know that these two are important causes of self-harm. So if one is not there, there is a high probability that the other could be there. That is why I do not want to adjust on colliders, because I am now forcing in a relationship between an exposure and outcome. Are you getting me here? This is the most difficult part to understand. Because see, you have to understand how compounding is different from self-harm. So I do not know whether screen time and obesity are associated with each other. When I adjust for parental education, for example, I restrict my study to children who have high parental education, and I study the association. So parents with high educational status, still I am not able to comment on the association of screen time. So I have a child with high screen time. I will not be able to say whether that child has high obesity or not, because this association is not known to me. Screen time and obesity association is not known to me. All I know is that all the children have high parental education. I am not able to make any guesses about obesity even if I know screen time. Another scenario is I do not know the association between screen time and obesity. But all I know is that screen time increases the risk of self-harm. Another reason for self-harm could be obesity. I know the self-harm status of the child. If the child has a history of self-harm and no history of high screen time, then I can guess that, okay, the other reason, that is obesity, could be there in this child. So even if I don't know this association, just by knowing this status, I am able to guess this association. That is why I am saying that if I adjust for a collider, I open a closed path. For the parental education, a pre-existing open path is closed by adjusting a potential confounder. Are you getting me at least some part of what I am trying to say?
Yes, ma'am.
So for those who are really finding it a bit difficult, I will share a few resources. You can go back and read about colliders, because Confounding, I think you all know about confounding and how confounding helps us make the adjustment and get to the true association. But colliders, why we need to be careful with colliders is because we should not adjust for them in our analysis, and hence if there are colliders we need to keep them aside. Now this Bergson's bias is another example of a collider bias. It's a selection bias where there is collision by stratification. So the example which was given by Bergson was about diabetes and cholecystitis. And he had done the study in hospitalized patients. Similarly, there is another example of locomotor disease and respiratory disease, again done in hospitalization. Now remember that whenever we do hospital-based study, we are restricting our study to hospitalized patients. So automatically, there is collision with hospitalization. If you have diabetes, you are likely to be hospitalized. Another reason for hospitalization could be cholecystitis. So for a hospitalized patient, if he or she does not have diabetes, then there is a high chance that the alternative explanation for hospitalization could be there. And that is why there was a negative association between diabetes and cholecystitis. There can be this, can be a positive or a negative association based on the criteria of hospitalization. But because you have restricted your study to hospitalized patient, which is a collider. Similarly, locomotor disease, respiratory disease, both individually, separately can lead to hospitalization. So remember that when you do a study in hospitalized patients, there is a very high risk of selection bias because you are going to get distorted results because hospitalization is a collider. That is, A causes hospitalization, alternatively B causes hospitalization. So you are restricting on a collider and opening a path leading to selection bias. Again, you will have to read more. There are many articles which talk of Bergson's bias as a collider bias. So remember that these DAGs, when you draw DAGs, they are essential when you want to do observational study or use observational study designs. And you want to use these study designs to establish causal associations. You have a clear exposure outcome and you want to say that A causes B, then that's the time you need to really draw your DAG before you go ahead even designing your study and then later analysis. What do DAGs do? They help us to depict our assumptions about various variables very clearly and transparently. So they help us to do it very, very systematically. What is our reasoning? What are our assumptions about the exposure outcome and how are the various other covariates associated with exposure outcome is what we want to show in our DAGs. And then say that these are the different variables which we have chosen and adjusted for these reasons, and we have left out these variables as they would have created a bias in our analysis. Remember that DAGs are not analytical tools. They are only helping us in our thinking process and then communicating our thinking process to the audience. That is something which is important. So again, if you look at age, exercise, and hypertension. Now here, age is leading to a backdoor path between exercise and hypertension because age is associated with exercise. It is a risk factor for hypertension. And in your DAG, you can see that the arrows also indicate that there is a backdoor path. Now, if you want to block the path, you can do this in your regression model by including age in the model. When you adjust for age, you get the true association between exposure and outcome, where now age has no role to play. Now in the DAG, usually see, you draw the DAG in this fashion, and whenever you put a square or a rectangle in that for that particular variable, in the DAG, it represents that you have adjusted for that variable or you have conditioned for that variable. So If you condition, then you block the backdoor path. Now, in this case, BMI is a mediator for the association between exercise and hypertension. So I told you, you have to be clear whether you are interested in the total effect, the direct effect, or the indirect effect. And accordingly, if you are not interested in the total effect, you will have to go in for what is known as a mediation analysis. But otherwise, we never adjust for mediators because you block the association of the exposure with the outcome through mediation by adjusting for mediator, because mediation is an open path. You close it by conditioning. So this is what we usually avoid. And then I had taken health checkup, but I need to, okay. But this, remember, I changed this to stress test because this will help you to understand collider, which is a difficult concept. Now, supposing a physician prescribes a stress test if there is no history of exercise. So the patient says he never exercise, and then there is more likelihood that the physician will say, let me do a stress test for this individual. Another scenario is where the physician prescribes a stress test if the patient has hypertension. Now see, stress test becomes a collider. So the exercise status or the history of exercise leads to stress test, hypertension history leads to stress test. So if you do not look at stress test at all in your analysis, you are safe, but you adjust for a history of stress test. So for example, if there is an individual with a history of stress test and he says that he does regular exercise, then you know that this individual has a higher chance of hypertension. You have another individual who has been told to undergo a stress test and he gives no history of exercise. Then you know that, okay, this person must have been prescribed because he does not exercise, less likelihood of hypertension. So in the reality, if you don't know the association between exercise and hypertension, by adjusting for stress test, you are opening this backdoor path. You are able to guess the outcome based on the exposure status if you know the stress test status of the individual. So this is a collider which you should not adjust for in your study, because there is a collider on the path. This is the collider. By adjusting this variable, you are going to open up this closed path and you are going to be able to hint what the outcome will be if you know the exposure status. Is this helping in any way? Anjana?
Ma'am, actually, may I ask you something?
Yes.
Like, if we are adjusting for stress test, we are opening the pathway, right?
Yes.
So in that case, we will be getting exercise is leading to, matlab, less exercise can be a factor for hypertension.
See, in our analysis, when we are doing analysis, what we want to say is whether exercise and hypertension are causally associated. That is, exercise causes hypertension or not on its own, right?
Yes. Yes.
So when we do not want any other variable to interfere with this association.
Yes.
Okay. So we want, in our analysis, if we find a positive association, then I should be able to comment on the hypertension based on the exercise. But now what happens is, if I know the stress test and I know that it is a collider and I know the status, that is stress test अभी उसको prescribe किया है. If stress test is prescribed, if I know the status, because stress test is a result of either no exercise or presence of hypertension, right?
Yeah.
So if stress test has been prescribed and I know this individual does not do exercise, just based on this information, I am able to say, okay, then there is less likelihood that the person has hypertension. Because I know
But
that hypertension leads to stress test, no exercise leads to stress test. So either of this or this leads to stress test.
yes.
So if stress test is there and there is no exercise, then I will conclude that there is more likelihood that there is no exercise, इसलिए stress test prescribe किया है, hypertension होने का chances कम है इस individual में, in that individual.
Ma'am, but we will get to know that only if we know there is an association between exercise and hypertension, right?
No. All I know is that exercise का एक reason, no exercise एक reason है stress test के लिए, hypertension एक reason है stress test के लिए. मुझे पता नहीं है exercise, hypertension are associated with each other or not. All I know is this. And then when I talk to the individual who has come for the stress test, I ask history of exercise. Based on that, I am able to say, okay, if they have come for exercise, hypertension nahi hoga. If they have not come for exercise, there is no exercise, then the other reason could be the reason for why they have been prescribed stress test.
Okay. Got it, ma'am.
Yeah, so this is a bit complicated. You will have to read more examples to understand collider bias. So either this or that or both, that leads to, the incorrect estimate. And that is why we are worried about colliders. So please, I'm just introducing these concepts. You will have to read more examples to understand what are colliders and how we should be careful about not including them in our analysis. So age is a confounder. I will include it. I would want to adjust it in my study. BMI is a mediator. That is what my DAG is telling me. If I'm interested in total effect, I will not adjust for it. Stress test is a collider. I will be careful to not include it and adjust for it in my analysis. So in your DAGs, you should be able to identify confounders, mediators, and colliders properly and take appropriate decisions. So in this example which we saw, therefore, age and sex were confounders, BMI was a mediator, health checkup, which I later changed to the stress test, was a collider, and all of them together where you're including everything. So this is what we tend to do. The last one which is there is what we tend to do. That is known as the black box approach. Include all the variables in the regression where you have the mediators, the colliders, the confounders, but that actually is not the correct way to move ahead. So you see that when you added the mediator, the protective effect dipped because much of the protection was through the BMI. If you adjust for BMI, then the mediated effect through BMI is lost. So the protection effect lowered. If I adjust for collider, the protector effect exaggerated. And if I put everything together, then of course it is going to be a mix and match and you will never get the true effect. So of course, what is the variables you want to include depends upon what estimand you are interested in. Are you interested in the total effect? Are you interested of the direct effect of the exposure and outcome without any mediation? You usually never adjust for colliders. So determining the mediators, confounders, and colliders are important if your research question is clear and you draw a DAG and then take a decision about what to include in your analysis. So compared to the traditional approach, how is this approach with a DAG different? Because without a DAG, you would probably include everything, adjust for everything, while here you adjust for appropriate variables. When you use a DAG, actually you identify your confounders a priori, and you don't even depend upon your p-values or 10% change after addition of a variable, which usually we do in our analysis. The most important thing is that when you think without a DAG and just include variables, there is a chance that you may introduce a bias because you may, adjust for a mediator or a collider. So you have to be very careful with colliders, mediators, then we move ahead with DAGs. You identify your confounders more systematically and communicate them in your DAGs. whatever assumptions you are making, those are transparent with a tag. And when you are using your p-values, we say it's a data determined model. But here it is the subject knowledge which helps us develop your model when you use tag. So these are the key differences when we depend upon our traditional approach or we use DAGs in developing our models. But are DAGs then the gold standard? Not at all. DAGs do not tell us what is true. There is no true DAG. We are only able to draw a DAG depending upon how much knowledge we have about the subject matter. So that is one limitation which we always have to mention, that whatever subject knowledge is there, background information is there, based on that the DAG was drawn. So however, this is still more, it's far better than going ahead without being transparent about your thought process about the various variables which you have included in your model. Sometimes people feel that DAGs are oversimplified. Sometimes when too many variables are included, it can in fact become more complex and then cumbersome to interpret. But still, we are reflecting the real world situation. So DAGs are actually what we are looking at when we learn DAGs is just causal thinking, how we should think about the causal association. We are not yet talking about any causal estimation methods or any statistics. It is just what we need to think and how we need to choose our variables. Now, I will not come here because I think we are becoming too heavy already. So I will go to an example, right? Now, this is a DAG. I will show you a way of drawing the DAGs using a software known as the Dagety software. Are you ready for it now? I don't want to overburden y'all, but I want to show you all a software which you can use to develop a DAG. For example, this DAG itself. So are you ready for that?
Yes, ma'am.
Yes, ma'am.
Okay, so here what you see is, you see that alcohol use disorder is the exposure, fire mortality is the outcome. And this green arrow which is there, this is the causal association. And all these pink arrows, they are the backdoor paths. So backdoor paths, I told you, are open paths. These light blue colored circles, they are the variables which are associated with the outcome. And if you look at the ones which are pink, they are associated with both the exposure and the outcome, which is our definition for confounding. So all these are confounding or backdoor. These are confounders and these are the different backdoor paths. Before we go to the software, can you tell me then what are the variables you will adjust for in this particular scenario? You are interested to know whether alcohol use disorder causes or increases the risk of fire mortality. That is your research question. So you have then identified all the potential variables associated with exposure and outcome. And you find some of them are contributing to backdoor paths. So which are the variables you will adjust for? Do you see any colliders here? Colliders means what? Any arrows going from exposure and outcome into any of these variables. Do you see that happening?
No,
Probably
ma'am.
no, because I have purposefully kept this very simple. So all these arrows which are going from exposure, from the variable to the exposure and variable either directly to the outcome or through each other. So all these become what? Confounders. And all these become then, because they are going directly, indirectly, in here or there, they are connected to each other, they are confounders. So which ones would you like to adjust for?
Confounders.
So can you name them?
Family history of alcohol abuse,
Yes,
friends' alcohol use, heavy
yes,
alcohol use,
yes,
essay.
yes. So this is socioeconomic position, okay, socioeconomic status. So I will show you how to do this using the software. So first I have to stop sharing. Yes, you are seeing my screen?
Yes, ma'am.
Yes, ma'am.
Okay. So this is the website where you have to go. This is Dagitty, DAGITTY.net. So if you go to this website, you go and try and understand the website. This was developed by this particular person, Texter. So you can go to launch Dagitty online. Are you able to see this?
Yes, ma'am.
Yes, ma'am.
Yeah. So just let me try and get this because, yeah. So you can see that you have different options which are given here. So this classic is the one which will give you your classic DAG. The normal mode is the one which we go in for. You want the coloring to be shown for the causal path, which I told you is green, then biasing path, and there is an ancestral structure which purposefully I have not touched upon. I will try and show you if possible when we go to the DAG. And then you have these color legend. So you have exposure, which is shown in green with an arrow. Then you have this outcome, which is blue with an eye in it. Then you have the ancestors for exposure and the outcome in green and in blue. And if there is a confounder, that is a variable associated with exposure and outcome, then it is pink. Then you have adjusted variable, unobserved, and other variables, and these paths, the pink, which is a biasing path, and the green, which is the causal path. So what you do usually when you want to draw your DAG is to go to model and say develop new model, and you want to now start adding your variables. So here you can see alcohol use disorder and 5-year mortality were your exposure and your outcome. So you just click and you say alcohol use disorder. So this is okay. This, if you select here and say exposure, it becomes green. If you want to add outcome, you say 5-year mortality. I will just say mortality, for example. I say okay. So my variable comes up. I select this this variable, and I say this is the outcome. It shows as the outcome. The socioeconomic position is another variable. So I say ACP. I say okay, and this becomes a variable. Now I want to say I'm interested in the association, so I click on the exposure and then I click on the outcome. I get an arrow from exposure to outcome, which is the causal association I'm interested in. I'm saying this SEP is associated with the exposure. As soon as I say that this variable is associated with the outcome, now this comes in pink color, which means that this is the backdoor path. Similarly, I can go on adding variables. So if I say family history of alcohol use, I add the variable. I say this variable is associated with this, and I feel this is associated with this also. I get a backdoor path. So again, this becomes a potential confounder. Are you getting me here?
Yes.
So you can try this out after the class. Now, as I'm doing this on the right hand side, you can see that I am getting this causal effect identification. So this is telling me what my exposure outcome is, and it is also telling me what are the different biasing pathway which are being developed for the association. Then there is the statistical language which helps us to understand conditional independencies, and then you also have the code. Now this code is also very interesting because I have developed the code for this association which is there. So all I do is, if I want now the entire DAG, all I do is, because I have the code with me, I just go on the website and I paste the code and I say update the DAG. So this gives me the entire DAG. I can pull the DAG anywhere I want and change the shape of the DAG. So I have now all these variables of interest. Now what happens here? Here it is showing me something known as minimal sufficient adjustment set. What this means is that there can be many variables on the backdoor path. I need not adjust for all the variables. There is a minimal sufficient adjustment set. If I adjust for those variables, the others are automatically going to be adjusted. Now what happens when I adjust for, say, these are the two minimal sufficient adjustment sets. So if I adjust for alcohol use, so I have to select the variable and I have to say adjusted. Then they're saying adjust for SEP. So if I take SEP and I say adjust for this, what happens? All the pink backdoor paths now have become closed, and I am looking at the pure relationship between the exposure and the outcome. So what this DAGIT is doing me is it's helping me identify this minimal sufficient adjustment set. I need not then take or collect data on these other variables. These two variables, if I am able to collect data on adjust for, all the other things are controlled for, and I am going to get to study the association I am interested in. Are you getting me here?
Yes, ma'am.
Now, supposing I just put some variable, say family stress, and I say, okay, now this variable is there. Alcohol use disorder can lead to family stress, mortality can lead to family stress. So this is a collider, right? Now, if I say I inadvertently I take all the variables and also family stress and I adjust for it. See, automatically what happens, it opens many, it becomes an open path and it opens many other backdoor paths. And it shows that this is incorrectly adjusted. I'm going to get a biased estimate. So if there is a collider, it is our job to keep it outside any adjustment or conditioning. We have to focus on these the variables in the minimal sufficient adjustment set and adjust for it. It will give us the true estimates. Is this clear?
Yes, ma'am.
You can also go and you can get to know more about this with help. So if you go to help, there is a manual and other resources out there. There are options for layouts and how to do how to add variables and do other things. You can rename the variables, you can delete the variables, how to make connections, and you can also save all of this in different formats. So that is also there. So they are saying you can copy paste, you can do that also, and you can have this export to different forms, and then the best way, of course, is to copy and save the code, because many times as we read literature, we come up with more and more variables. So if you copy and if you keep your code properly, you can always come back and make edits. Once you save it as a figure or something, then you can't do any edits. So this DAGIT is very useful when you want to build your DAG before even you think of your design and your analysis. So right from the time you start thinking about your research question, especially one exposure, one outcome, and clear-cut association and observational study, this DAGIT can help you. If you are interested, I can show you a little bit more about this minimal set, because that is also interesting. You do not really want to include all the variables, not even all the confounders for adjustment. You have to just identify the right set of variables. That is the minimal sufficient adjustment set. And this DAGIT helps you to do it very easily. So this DAGIT, when it's identifying this set for us, what it does is it blocks all backdoor paths, identify the variables which you condition, and block all backdoor paths. At the same time, you do not want to block the causal path and you do not want to open collider paths. So when things get complicated, it does it automatically for us, given that we have identified all the variables and shown it properly in our DAG. Because it removes unnecessary, confounding which is there, and also then helps us pick the right variables for which we need to collect data and then include them in our analysis. So I think I will stop here. If you have any questions, I will just first, let me just go back and any questions from your end?
Ma'am, chat box is empty.
Okay.